So let's look at the limitations and the future research. Transformer models have gone a really, really long way, but we are still at the same time in the process of evolution when it comes to the entire AI space. If you compare that to the internet and the other technological innovations, I think the AI system, since it came into the public space, has been improving, and it's improved very exponentially within a very short period of time. So, given that, even though that the transformer model has been able to give us very, very good results, it also has its own limitations. I'm looking at the limitations now. So we have challenges that when it comes to the quadratic complexity, the self-attention costs. With much sequence like we just like go to O of n, very huge squared O of n, and that's very long processing time with more sequence or context length. Now we also need very good memory requirements. So we need good GPUs, we need good TPUs, we need good LPUs, whatever you're using. But infrastructure processing unit that will get to consume, we need very good quantity of that. But the good thing is that the parallel processing of the transformer architecture is able to enable us maximize or optimize the use of this infrastructure processing units, the CPU, the GPU, whatever. We're able to maximize the parallel processing capability of GPUs, of TPUs, and training our data. So here's heard about TPUs before. I know everybody said about CPUs and GPUs. TPUs are more of the tensor processing unit. So the more of like the tensors are what? What are tensors? It's just a technical way of saying matrices. Matrices are what? Collections of what? Vectors. And these vectors are what? These are the embeddings. Embeddings you get from what? From our tokens. And tokens you get from what? Our data. So this is how we just derived downlaying, and we're able to use that to learn about the context and meaning of data, and use that meaning that we've learned, that pattern we've learned from this data sequence to be able to give future predictions that are very accurate. Now, we also have very ongoing active research. We have new architectures that aim to solve these issues: sparse transformers, linear attentions, efficient long context models. So we're having longer context models now. We haven't, compared to what it originally was when the architecture came out newly. Now we're having longer context, longer models that are able to have deeper networks and also train on larger amounts of data and a very large context window. Because the more context window, the more context of data inputs it's able to process at a given time in parallel. That gives us more, the more its ability to predict the next token accurately based on the existing context. Now, this gives me two highlights just briefly about the pre-trained transformers, pre-trained models, pre-training and post-training, and then the racks. Just in a very, very good high-level overview. The pre-trained models are models that we trained on basically the internet, basically on an enormous amount of data. So be the internet, even if it's a small language model that is just basically your own data set, it's also like being trained on very huge amounts of data. Mostly the data must have been synthesized to be able to be structured. However, it's not always structured. It can be structured or unstructured. Nevertheless, we still have tools that aim to structure, be it from the internet, is able to structure these data sets so that it can be able to be passed into these AI models. So the pre-training involves like training on very enormous, arbitrary, large data sets. Post-training deals more with fine-tuning. So fine-tuning now entails that now I've been able to train on the internet. I've been able to feed this model so much information. It's able to have, by doing that, it's able to learn the fundamental concept of how the actual real world works. That's the whole aim of it. The aim is not really like to make it to learn everything, because it's not going to be able to do that, given that it's learning so many things at the same time. It's just going to be able to capture the underlying principle of real world patterns. So it's able to know that in the word THED, the H always comes after the word T, and the E always comes after the word the H. So it just lends arbitrary real world patterns and information. That's what pre-training helps. And in doing that, since it's trained on a very enormous chunk of data, it's able to learn about different things in different ways. Then with post-training, with fine-tuning, you're not able to say, okay, I want to give you more context about this particular field. So you're able to have more information about this particular field, and you're able to give me more accurate results, more accurate outcomes or outputs based on this fine-tuned data I'm passing into you. So giving your knowledge of the real world, giving your knowledge of how the world actually works, and giving this knowledge I'm passing into you, which is more structured towards this particular problem, you're able to give me better outputs. That's the whole concept. And then we also have the RAG, retrieval augmented generation, where you're basically context injecting, but in a more defined and optimized manner. So unlike just passing context, maybe a summarization or conversation history into the model, with RAG, we're not passing arbitrary or random conversation or context history. We're passing well-defined context that suits to the prompt that has been passed or the input. So that let's say you have a company and your company has data that pertains to the company, but you also want your customers to be able to query and get information about your company. So you have two options. You either train the model, you either create a transformer model and train that on your company's custom data, and that entails that you just need to have very good amounts of your company's data for you to be able to first learn about reward patterns and then use those reward patterns to be able to give you prediction based on your data. Or you can use pre-trained models that have already learned about the world, and then you pass your company's data into it, either by fine-tuning or by RAG implementations. By RAG, we have retrieval augmented generation, where we're passing my company's data and I store that in what we call a vector database. So that's a different topic for a different day, but it basically stores my data as vector embeddings, and we use several vector search operations to be able to retrieve context based on the input. So based on my prompt or based on my question, it's able to go and fetch out the particular parts of my data that correspond to my input, to my question. So it does that by using multiple operations, be it cosine similarity score or whatever similarity score or algorithm you choose for it. So it's able to use that to fetch the actual response that fits to your input data, that fits to your question. It's able to just retrieve out of the bulk of company's data. It's able to give you just a specified streamlined context that matches your prompt, and then it passes that into the model, and then the model uses that as context to give you a response. So it's a very interesting flow, very, very interesting flow. And the whole concept is just basically mathematical and very logical. It's very logical. You're just mapping real world situations into computer machines, and you're able to do computations on that. And these computations, you help to store information in neurons or just like bytes of data, basically nodes, and you now use those nodes as learned patterns to be able to create new patterns or create new information from that. So very, very interesting subject, very, very interesting logic, and the transformer parallelism that is introduced to us gives us very good efficiency when it comes to doing this. Now let's look at the applications of transformer models. Transformers power modern AI systems. They include natural language processing. I know everybody's been hearing about NLP. I know that everybody's been hearing about NLP everywhere. Natural language processing. So it's, I believe, for the LLMs or the large language models, the AI models, to be able to learn about natural. When we say natural, we mean what? We mean human languages, human context, sequences of data in human patterns. It's able to learn about that and use that sequential data, learn about sequential data and use that to give output. So it's also been used in chatbots, machine translations, where you have a language, you want to interpret that in a different language. That's where the entire encoder and decoder system in the transformer network comes into very good play, as compared to only encoder or only decoder. The combination of both gives us a very good output system when it comes to machine translating one language to a different language based on some learned patterns. Computer vision, as I mentioned previously, like the transformer models have also been inculcated into like CNNs. We have like mixture of CNNs and also transformer architecture that's been able to give us very good outputs. Very, very interesting logic being done there. We have vision transformers, CNNs and transformers all combined in different architectural principles, but very good. We have multimodal AI. So here you said about multimodal AIs. These are AIs that are able to both learn about sequential and spatial data. By spatial data, I mean like images, where data is not like in a given sequence. Every entity of the data is in space. So you have like multiple, for example, we're talking about RGB encoding of the pixels. You have multiple RGBs, and this is all spatial. So how do you now get to learn about when it's spatial as compared to when it's just sequential, as in like text? So we now have LLMs that are also multimodal and able to learn in spatial data and sequential data at the same time, all thanks to the transformer architecture. And we also have text plus image models. Finally, we're looking at the conclusion. So I hope that this session has been very interesting and been very, very useful to you all. And you have been able to get very good context about how all these models work. So it's no longer like magic going on. It's no longer magic going on. This is real logic. It's nothing super complex. It's just based on foundational logic and mathematics and statistics. So when you're able to combine all this, you will be able to map any real world entity into computer computations and use that to gain real results, real outputs. So the transformers revolutionized deep learning by removing sequential computation, introducing scalable attentions, enabling modern AI systems. Today, they form the foundation of generative AI and LLMs. Future research focuses on efficiency, longer context, and multi-modal intelligence. And that's where the AGI, artificial general intelligence, comes in. So the aim is that in the future, we want to be able to have a system where a singular model is able to be it becomes an expert in multiple fields, as compared to where you have to fine-tune for specific fields. We want to be able to have one singular model, or just models that by architecture, by processing, by computation, they're able to be very good in multiple fields and give very good results without having an SLM or maybe a custom trained model. So one model is being very good at healthcare, the same model being very good at tech, at science, at finance. So all these multiple sectors, one model is able to be very good at performing multiple operations, just given one specific architecture. So that also this is where the whole system is heading towards. We have all the agentic AI systems. I had that in my previous talk, and even when we are building at LaserVolt, for example, you see where agentic systems are being used for voice processing, text narration, chatbots, where, for example, in the banking system, when you go to LaserVolt app, in the banking system, you're able to see where you have real conversations with these bots, be it voice conversations with the agents, or be it text conversations via chatbots. You're able to do real conversations with these bots. And the most interesting part is that you might not even know that these are computers. You might just feel that these are human beings, because these models have been able to learn the conceptual intricacies of human behavior, of human voices, of human intellect. And I can tell you, I can keep giving you more and more examples on the multiple evolutions. When it comes also to vision, we have the Sora T, we have the Kling, we have very good AI models out there. We have VO3, we have very good models that are coming out there, all still based on these foundational principles, but have been able to give very amazing results. Progressively, we're seeing very good progress going on, and I know that progressively, like, we're gonna have even more accurate models that beat by all dimensions, beat human intelligence. And we're also looking forward to like times where we get to have better accuracy when it comes to integrating all these models or all these AI agents into the biological neural networks or into the human brain, and having very good synthesis and synchrony when it comes to the digital data processing and the biological data processing. So agentic AI has paved that system. Transformer Network has created that foundation for us. We have agentic AI progressing and evolving in a very, very fast pace. So I hope to see what you all are going to make out of this, and I hope to see that going forward, you understand the basic infrastructural principle of how all the big models you see out there, be it open source, open weights, closed source, closed weights, vision or text LLMs, are models out there. When you see them, know that they are not magic. They are simply mathematical computations on learned real life data. So thank you very much for coming onto this session. I do hope that you had very good understanding of the subject, and I do hope to see you in our very next session. So bye.